Okay, so everyone, welcome back to the video lecture series on network theory. This is revision class lecture number 62, and we shall continue the question paper problem solutions. So what we have discussed yesterday. Okay, so one problem we have uh, not solved completely yesterday, so we shall take that and let us complete that. Okay, so that was based on Laplace transform, right? Okay, so if you go through that particular question, so it was from the year 2004, right? So regarding this problem, so let me write it. Okay, so we were having this circuit, if you remember. So we have this circuit, a voltage source followed by a resistor, sorry, okay, let it be a resistor, then inductor, okay, then one more resistor was there. Okay, so we had a switch here, right? Okay, current I was given. So this problem was asked in 2004. So what is the requirement here? We have to solve for I of t. To solve for I of t, right? So if the switch K is opened at, if K is open at t equal to 0, okay, and before the switch operate, before that, what was given? Before that, circuit is in steady state. So if you go through the yesterday's assignment, so same circuit I have given, but instead of V and all, I have given you the values. So already first condition we have solved, that is, first we have to analyze when t equal to 0 minus. So if at t equal to 0, if it is open, at t equal to 0 minus, switch K will be closed, right? Okay, so if it is closed, so what we have seen is, if you consider the circuit behavior initially, so if it is closed like this, this will be the circuit what we see, right? R1L and R2, K is closed. Okay, now if you use the definition of initial conditions, so what we observe is inductor will act like a short circuit. Okay, then if you consider the condition over here, this particular point, so this current will be coming here, and here we have the least resistance path compared to this point. So current will tend to flow like this, right? So after this, what we get is this circuit. So R2 can be neglected for that moment when K is closed at t equal to 0 minus. Okay, and correspondingly, what we have, this current. Okay, this current we can call it as what? I of 0 minus. Okay, so this I of 0 we have already evaluated, so that will be how much? V by R1. Okay, and since the current through the inductor cannot change instantaneously, So what we can write is IL0 minus will be equal to IL0 plus will be equal to V upon R1. Okay, so this we solved it yesterday till here. Now if you take the second condition after this, okay, that is second condition is when t is 0 greater than or equal to 0, or we can say 0 plus. So here if you consider this condition now, so we can we can get back our inductor, we can consider the inductor back into consideration, right? And initially what is the current through the inductor? So if you make a note of that, IL0 minus equal to IL0 plus is V upon R1. This is the initial current. Now if you take the condition of the switch, K will be open or closed. Now earlier it was closed, so now K will be open. So if you draw the equivalent circuit here first, okay, let me draw the equivalent circuit first. So I will put the box here, why I will tell you. Then we have R1, then we have R2. So switch is open now, okay, and whatever you are analyzing, let it be I for a while, okay. Then if you transform this to Laplace domain or Laplace network, so what we get is V will be V by S, and inductor, how inductor should be replaced here now? Inductor followed by its initial current in terms of the voltage source, okay. Then you have resistor, first resistor and second resistor, okay. So there will not be much effect on resistors R1 and R2, they will be as it is. Inductor will be replaced by SL and its initial current what we had. So how it will be replaced? Initial current in terms of voltage, in terms of current means you have to V is equal to I into R, right? Current we know it is V by R1. Instead of R you have to consider the impedance L, so that is it will be L into V divided by R1. So this is the condition for this. So is that clear now?
Yes, sir.
Yes, sir.
Yes, sir. So this we write it for reference, but actually in terms of the what you say Laplace domain, it will be I of S, okay. So if you apply KVL to this now, so what you get is minus V upon S, go clockwise, then we have is plus, let me multiply this current directly with the impedance parameters. So we have this R1, R2 and inductor. So it will be SL plus R1 plus R2. Then you have one more voltage source, that is L into V upon R1 equal to 0. Okay. So you have to solve for what now? I of S. So that I of S will be V by S plus L into V upon R1 whole divided by SL plus R1 plus R2. So here onwards you have to use the partial fractions here. So if you use the partial fraction over here, So what we can write? We can write I of S equal to P by S plus L into V upon R1 divided by, I can write like this, R1 plus R2 plus SL will be equal to. So how to split it now? So if you want to cancel this L term, so I can divide by L both numerator and denominator. So what I will get is V by S term, if I take it separately, so I will be getting like this, V divided by L, this L will this S will go down, so I can write S into S plus R1 plus R2 R2 into L. Okay, getting this step now, everyone? I have divided both numerator and denominator by L so that I can cancel out this. So this S will come down here, this L will cancel out with respect to this term, then plus V by R1 whole divided by, what you can write is, yes, again S plus R1 into R1 plus R2 divided by L. Is that clear now?
Yes, sir.
So this part we can solve it now by partial fraction. So that will be equal to A by S. How many terms are there? This S is there. So you can take it outside. Then plus B divided by, see this is now what we have is V upon R, a term, it is like a constant. So this you can, this entire term you can neglect. So you can apply partial fractions to this only, not this one, sorry, only to this. So that is one way. Plus B divided by S plus R1 plus R2 divided by L, and this constant term you keep it as it is, S plus R1 plus R2 divided by L. Okay, so if you solve for A, that will be nothing but you can take here, if you equate, so what we have is V by L. Okay, so V by L, this term, because we are applying that only to this term over here. Okay, so V by L you will get whole divided by, what we can write, S plus R1 plus R2 divided by L, for S equal to how much now? If you want to evaluate S, if you want to evaluate A value, so if you want to cancel for S equal to 0, so that implies A will be equal to how much? V divided by R1 plus R2. This L and L will cancel out for S equal to 0. Getting this? Okay. So next what you get is, for to solve B, again B will be V divided by L, so this term will vanish, so we'll get S only. So this is valid for S is equal to, if you want to cancel out this term, so you have to add minus R1 plus R2 divided by L. So if you put here s equal to minus r1 plus r2 divided by L, so that implies V will be equal to V minus V divided by r1 plus r2. Okay, following this everyone?
Yes, sir.
Yes, sir.
So finally I can get back to my I of s term here. So how I can write I of s? That will be a value is V by r1 plus r2. Then what we have is 1 by s. So we can refer to this. Okay. Then b is negative, so hence b divided by r1 plus r2 multiplied by 1 divided by s plus r1 plus r2 divided by L. Okay. Then this other term we can keep it as it is, s plus. Okay. So now if you take V by R1 plus R2 as common, okay, so what you get is, okay, not sorry, not this term is common. If you take the inverse Laplace transform, so we can solve for I of t. So 1 by s is nothing but it is for u of t. So u of t is always 1. So it is actually u of t unit step. So this will be 1. So keep it as it is, minus v divided by r1 plus r2. Okay. So this how you can write now? 1 divided by s plus a. If it is there, how do we write? It is e to the power minus at, right? So a is r1 plus r2 divided by L. We can write e to the power minus r1 plus r2 divided by L into t. Okay. Similarly here, v divided by r1, this will be e to the power minus
R.
yes r1 r divided by L into t. Okay. So in the assignment I have given you the values, you have to put those values there. That's all. Okay. So now you can take this common factor, what I was telling, v divided by r1 plus r2. So you can write 1 minus e to the power minus r1 plus r2 by L into t. So if I take v divided by r1 plus r2 as common, so here you have to just make some adjustment here. So if you multiply by what, you will get back v by r1. So if I multiply
R2.
it with r1 plus r2, right, divided by r1, if you multiply v r1 plus r2 divided by r1 to this, so we'll be getting v by r1 only. Are you getting this point? This I am replacing with respect to this. Is that clear, this one?
Yes, sir.
Then e to the power, you can take r1 plus r2 by L into t. Okay. So that will be equal to, you can keep this as an answer. Otherwise still you can means solve further like r1 plus r2. So again you see this term is common, e to the power minus r1 plus r2 divided by L into T. So if I take e to the power minus r1 plus r2 divided by L into T as common, so what I can 1, I can write minus r1 plus r2 divided by r1. Okay, so this will be further v divided by r1 plus r2 1. Now how I can write this now? Can I write like this? Check this. 1 plus, okay. If you take the logarithmic concepts, can I write like this? R2 divided by R1. Then e to the power minus R1 R2 by L. Sorry. Okay. So sorry, R1. This one, can I write like this now? This term I have taken common. These two things. So what I will get is this one, R1 plus R2 divided by R1. Okay. So what I have made here, understanding this? So you follow the same thing in terms of the assignment what I have given. Okay. So another question. I think that equation we have solved, that waveform we have solved yesterday, right? Okay. So now if I take one more question here. Okay. So in the assignment, what I have given is uh, this circuit. If you check that, so this we have already solved with values A and B. RLC circuit it is. Okay. So this is again a question paper problem only. Okay. So this one we have solved these kind of problems. So can you go through that initial condition? Then what you have is the question, find the Laplace transform of delta t e to the power minus at and u of sin omega t and u of t. So those derivations you have to do. Then Laplace transform of sawtooth waveform. So in the assignment I have given some values, right? So this sawtooth waveform, what I have given, this value, these values are t and a. So if I take it as 2 and 2, so how to solve it? Can you tell me this f of t equation now? First step is what? First you travel from here? 0. At 0, is there any change in magnitude? No. So it is changing by steps. So you will get a ramp. So if I call A to B, you have to analyze the slope. So step number 1 is you get the slope of this. So how much will be the slope now? A to B.
1.
1.
1.
1.
Somebody is telling point.
1, sir.
Yeah, it is 1. So we have solved enough problems with the slope. So just go through that. So after this, now you are at point B. You are at point B. So here you have a slope of 2, right? Sorry, slope of 1. Then where the things are changing. So from here, you are not continuing like this. From B, you are getting down. And what is the magnitude here? 0.
0.
Okay. So how to solve it? A to B slope is 1. So f of t equation, you have to split it from A to B is what? Then plus or minus B to C is what? Then plus or minus after C. Okay. Like that, you need to solve here. So if I just okay, fine. So then plus or minus C onwards. So A to B, we have a ramp signal here, right? So I have to write, how do you write it? Slope multiplied by that ramp. Yes, ramp starting point. Then plus or minus B to C. Now B to C, you are going down, you are stepping down. So it is like this, a step signal, right? Unit step signal or a step signal. So if you consider that step signal, so what you need to do, you have to first stop the ramp. Where you have to stop the ramp? At point B. Okay. So if you want to stop that ramp, earlier slope was 1. So you have to decide here how much slope and the where you want to stop that. So that you have to write it here, right? Stop ramp at which point? Then plus or minus, now you are seeing that the step function is you are getting. So you have to write magnitude followed by its starting point. So if you follow like this, what we have slope here 1, where ramp is starting at point 0. So you have to write r of t. Getting this? Then if you want to stop that ramp which is continuing, You have to stop at point B. So here, what is the value? It is 2. So with how much slope you have to apply? Previous it was 1. So to make it as -1. Then here R of, you are stopping at which point?
-2.
T
T
minus.
-2.
Then you are getting into the slope 0. So again, here, what you have to do here now? So magnitude is 0. So earlier it was, if you take this magnitude, it was 2. So 2 to 0. So what I need to add here?
minus
This point
-2.
magnitude is 2. So we have to add -2. -2 into u of, again, t minus 2. Getting this?
Yes.
yes.
So I have given you many kind of waveform synthesis methods. So whichever you feel easy, you can do that. And same question, if they to synthesize using gate signal, then what you will do? If they ask you to synthesize this using gate signal, then you have to multiply this with a gate signal which starts at 0 and ends at 2, and always remember gate signal will have the magnitude of 1 only.
1.
So this you have to define with respect to this only. So there you need to make some adjustment like what we have done in the earlier problems. Okay. So fine, no issues here.